Okay, so today we're moving on to an application of vectors, things that we can use vectors for, so force and tension. So first of all, some definitions. Force is push or a pull, and direction. So, if we need to add forces together, you need to use the usual things. Right, we'll get to that. Mass is amount of material in a body, and it relates to its density. Alright, the next thing is weight, and this is where, in science, and that mass and weight are different things. In everyday language we call them the same, but in science and maths it's different. So weight is the gravitational force. So it's always down towards the centre of the earth, and it depends on mass, so how much material, and gravitational strength. So the weight turns out to be mass times gravity. So your weight force is m times g. It's going to be down, and on Earth, g is 9.8. Newton per kilogram. Okay, 9.8 newtons for every kilogram. Alright, the next thing that's also in that heading, tension is it's a force. So it's nothing special other than it's a force in a string or a wire. Alright, so it's obviously it's going to be stretching the thing out. So let's have a look at an example. Simple one. Weight of a 3 kilogram mass. Alright, and there's just mentioned back here, page 1 there. Weight is m times g. So it's m times g. The mass here is 3, and g is 9.8. And 3 lots of 9.8 is 29.4 Newton, and the direction would be down. Now, alternative, so it would be 3g Newton, where we're just leaving the g in there instead of putting it in the number. So just be aware of that just when you're looking at your questions, in case, depending on what form they have. Okay, another a mass of say 0.5 kilograms, added to a mass of 200 milligrams. What is the total weight? Okay, so remember weight equals mass times G. So we need to know the total mass. 0.5 kilograms plus milli means 10 to the minus 3, so it's 200 milligrams. We're going 1, 2, 3. That's where our decimal point ends up, so plus 0.2, 0.7 kilograms is what we've got. So 0.7 times 9.8 is 6.86 Newton. Down again. Okay, so that's that. Let's look at another example. Okay, so here's our mass, 10 kg, and we want to find the tension. Alright, so we're going to think about what's going on here. Now if that's hanging there, gravity's going to work on it, it's going to have some weight, the tension is going to be holding it up, and you would assume then that what we have here is equilibrium. But anyway, so if we have equilibrium, what that means is that the tension equals the weight in size, but opposite in direction, obviously. So the weight is mass times G equals 10 times 9.8, which is 98 Newton, down. So what that means then is that our tension then would be 98 Newton up. Alright, the last part is what we call resolving vectors. So basically what that means is splitting them up into bits. So if I have, say, an X and Y plane like that, and I've got a force F at angle theta, then I can split that force at F up into a whole bunch of different ways. Now, the most useful way to us, because there's an infinite number of ways you could do it, but the most useful way to us is to have horizontal and vertical components, where those horizontal and vertical components form a right angled triangle. Now when that happens, it's just simple trigonometry. This one is F sine theta for the vertical component, and the horizontal is F cos theta. Alright, so those perpendicular ones are by far the most use to us. So let's look at an example. Okay, so there it is. So horizontal and vertical components, basically we're talking about I and J components, aren't we? So our horizontal, which is our I component. So our horizontal bit would be, call it FH, will be 5 cos 30 degrees, which would be 4.33 Newton, and our vertical component would be 5 sine 30 degrees, and that would be 2.5 Newton. Alright, so there are our horizontal and our vertical components. Alright, so that's it for exercise 14A, which is problem set number 6 on the list. So good luck with that.